So in number 59, we have a charged particle that's either an electron or a proton is moving rightward between two parallel charged plates separated by a distance of 2 millimeters. The plate potentials V1 is negative 70 volts and V2 is negative 50 volts. The particle is slowing down from an initial speed of 90 kilometers per second at the left plate. Question A, is the particle an electron or a proton? Well, if you think about this, the electric field in this case must be pointing towards the left. How do we know that? Well, if you think about it, this plate is more negative than this plate. And again, remember, electric field lines are always pointing towards negative charge, away from positive. In this case, the field must be going that way. What is that doing? Well, it's producing a force, or we can think about it for a bit. If this particle is slowing down, it must be feeling a net force acting against its motion. Since this force on this particle is in the exact same direction as the electric field, we know this must be a positive test charge. And so the answer for A, this thing is a proton. Question B, at what speed does it have when it reaches this? Now, a couple of quick notes on this one. You could actually use kinematics, regular motion, to solve it. Why? We can actually calculate the electric field. It would be negative dV over dx. In this case, we actually know the voltage difference is 20 volts, and the distance between the two plates is 2 millimeters. So you could figure this out, figure out the electric field just by doing that. Once you do the electric field, remember electric field is defined as the force per charge. From that, you could actually plug in the charge of a proton and you could calculate the force on it. It would just be equal Q times electric field. Now, once you know the force, you could use F equals ma and look up the mass of a proton, and you could actually then calculate the acceleration. And then finally, because you know the distance, you could do V final squared equals V initial squared plus 2a delta x, and actually calculate the final velocity. That would work perfectly well and would get you the right answer. But we always know when you're dealing with something like this with velocity, you can also use energy. And so that's what I'm going to do. In this case, the initial energy is just the kinetic energy of this proton, and the final energy is just going to be the final kinetic energy, plus the work done by the field. Now, how do you calculate the work done by the field? Well, remember, voltage is defined as work per charge. And if you rearrange that, work is equal to Q times delta V. And so I can plug that into the work in the kinetic energy work equation. Doing this, and don't panic, there's a lot of numbers on this one. Let me just walk you through it. The initial kinetic energy is just this. And you're like, wait, what is all this? Well, this is 1/2 mv squared. This is the mass of a proton, and the initial velocity is 90 kilometers per second, which is 90,000 meters per second. The work being done is this. It's the voltage difference, which is 20, times the charge on a proton, which is 1.6 times 10 to the negative 19th. So we've got this piece right here. And now you might say, wait a second, why is it negative? Well, think about this. We know the work must be negative. Why? The proton's moving this way. This is our displacement, delta x. And because displacement and the force are in opposite directions, this electric field is doing negative work on this thing. The angle between the two sides is 180 degrees. And so you're going to end up with some negative work. And then finally, our final energy is just kinetic. And so it's 1/2 mv squared again. But in this case, we're looking for that final velocity. Now just doing some algebra. The first two terms reduce down to this if you do the calculations. Combine those together, gives us that. Dividing both sides by that 8.35 times 10 to the negative 28th gives us this. And then finally taking the square root of both sides gives you this. So it'll reach the other side still moving about 65.3 kilometers per second, which is a little bit less than, or somewhat less than what it started. Yes, you would have gotten the same answer up here. Um, I don't know if it's less work or more work. I always find energy a little bit more elegant. I hope this helped. Good luck.